So let's start over. So sequences in metric spaces, meaning that we're going to do it in the abstract. So once in a while we'll go back to those examples and confirm that everything working out. But we will be speaking in terms of abstract spaces as they define. So we have a set, and we have a function, and we have those three axioms. That's all we've got, and we want to prove things that we know in calculus in a manner that is purely abstract, and so the details will be gone. So if you might see some of these ideas in calculus 1 or 3, but we will strip them off all the details that are not important. So if we're studying sequences and limits, which is what it's about, then let's strip off all the things that are not unrelated to limits and sequences and convergence. So for example, it turns out numbers are really, the fact that those points are numbers is not important. Distances matter. Okay, so that's the switch that we do here. This is the step, the crucial abstraction step. So if you start with the real numbers, calculus 1, and then you switch to metric spaces, what happens? Not a lot. Not a lot. As you can see, all you have to do is just to interpret the definition of that convergence of a sequence, calculus 2 or 3, and just realize that what you're talking about here, xn minus a, does this definition look familiar? There at the top. So xn minus a less than epsilon. Okay, but what is it? It's simply a distance between xn and a in R. Okay, so that's how we measure distances on the real line. We just subtract, take the absolute value. Okay, so we don't even have to worry much about the multidimensional spaces. We already have the idea right there. The idea is the word distance, and so we already know how to handle distances. So let's just remove that particular what I circled there at the top, and remove that idea and replace it with the word distance between xn and a. And that gives us what we want, and so that's what you have here. The distance in a metric space, we don't need anything else. Xn are simply element of that set, and a is an element of that set. Okay, and then we have a definition of a convergence right there. So xn converges to a when for every epsilon there is an n such that for all n larger than n, the distance of xn to a will be less than epsilon. And that is the picture. That is a picture illustrated by, so our abstract idea is illustrated with the two-dimensional situation on the plane. That's what convergence is. So all you have to do is to worry about the distances from a to x to these values x, to these points x. Okay. If you think about it, that picture could be just as well be three-dimensional, four-dimensional. You don't really know. It's an illustration after all. Okay. The very convenient step here is the next one. This is a very something that makes our life easier, and that is simply to realize that distances are numbers. Distances are numbers. So which means that this is a numerical sequence. And we already know how to handle numerical sequences. These are numerical sequences. So convergence of a numerical sequence is understood starting in calculus 1 or 2. Okay, so then that's what in the purple there is what we're talking about. So convergence will be simply convergence of distances. The end. So as long as the distance converges from xn to a converges to 0, then xn converges to a. Okay, so we have right away a definition that is matches our idea of convergence of distances. It relies entirely on the definition of convergence of numbers. Okay, so that's calculus 1, 2, and it also can be easily matched with whatever you saw of that matter in calculus 2 or 3. So convergence of points on the plane, three-dimensional space, doesn't matter as long as the D could stand for anything now. So whatever the space you're dealing with, it is equipped with the distance, and then you just use the one that is appropriate. So whether is it Euclidean space? Maybe. What dimension? If it is, then what dimension is doesn't matter. It works out fine in any dimension. Okay, and then it could be taxicab, it could be curved universe, doesn't matter. All of this works out. Okay, and then so this is then the definition. Sequence is just a function, so that was something of a discussion. To remember that after all, what if we want to once again interpret everything in a set theoretical way, then then a sequence is a function. Everything is a set or a function, so a sequence is not a set or a subset because the order matters. Okay, so it is a function. So you can see it here. That's why it is a function. Okay, so and then the limit. The limit is defined, as you can see. So once again, definition is entirely within metric spaces. So we have XD a metric space, a starting point, and then we have a sequence in X. Okay, sequence of elements, and then we have another element A in X, and then we say that xn converges to A if distance xn to A goes to 0. So that's all there is here. Okay. What happened next? So now the next discussion is the discussion of of the definition itself, making sure that it makes sense. And the one part is, remember, after every definition, the discussion is whether it is well defined, and the two questions are existence and uniqueness. The existence we know is not necessarily the case, so no matter what the space is, there are divergent sequences. Okay, so there. And I have examples there, so we don't have to worry about that. That is assumed to be the case. But as always with property, a concept defined by means of a property rather than specifically pointing out what it is, there might be more than one satisfying that property. So to say the limit then has to be justified before you use that language. So is it possible to have two distinct limits? We know that it's not the case in R. We also could make a case that doesn't happen elsewhere, but we rather go straight ahead and do it in an n-dimensional case. So there can be only one limit. Okay, so that's where we are. This is just a reminder of what the proof is in dimension 1, or for among the real numbers. So as you can see, there hypothetically you have two limits, and how do you demonstrate that they cannot be limits of the same sequence? And the answer is to separate. The idea is to separate them by intervals. So that's what you see on the left. Two intervals, one interval, the other interval. They could be large or small. That doesn't really matter. And then they are epsilon wide, or 2 epsilon wide rather, intervals. And then the sequence, according to our definition, the tail of the sequence, these are the tails, has to fit within that band, or within that interval. Okay, so and it cannot fit into both because they are separate. The way we proceed now, we concentrate on this part. This is what we care about really, because the notation, we don't see the n-x's anymore. So if we are speaking of x, this is what we do. We have A, we have B, and we separate them by what? That's the key question. So we still want to separate them. That just the question becomes what? Considering that the space is abstract. So what do you separate it by? And the answer is, and the answer comes from I guess from R2, and you separate them by disks. So you put two disks around them like this, and then what is supposed to happen is once again the same idea here with our definition. It has to have the tail of the sequence will be within one or the other, and it cannot be simultaneously in both. Okay, so that's the idea. That's how you prove it in R2 or R3 or R4. is you put two disks. If the disks are small enough, they will not overlap, and then they both have to contain the tail of the sequence. Eventually the sequence is supposed to end up inside of that disk, and it will not. It cannot end up in two disjoint sets. Okay, so that's the idea. So the idea is the sequence cannot end up in two disks if, so these are two, if they are disjoint. So what is that, how we do proceed in R3? Well, disks are replaced with balls. That's the language as it develops into Rn. By the way, in Rn we still use the word balls. Remember, open balls especially. Remember that in the calculus 3? Okay, so separating by open balls in dimension 3, it is literally balls that are not small enough so they are not overlapping. So and that idea works out again. But once again, it's just an idea. If you want a proof, you need to more than that. And for example, to begin with, would be a good question: what is a ball in the first place in a metric space? What is a ball in a metric space? And all you have to do is just to go back to the definition and find out what it means. As you can see, in R1, it was actually an interval. So we are developing dimension 1 at a time, from interval to disk to a ball to n-dimensional ball. Okay, so what is it?
It's everything that's less than a certain distance.
From that point. So we'll just define it for our convenience. It will really help us out a lot if we define these balls. So given a metric space, XD, so ball centered at A in X of radius R greater than 0 is the set. B usually AR. So it is a set of all X in X such that the distance X to A is less strictly than R. So this is an open ball. You can have closed balls as well, but let's say it's an open ball. Okay, so that will be helpful. The idea will be applicable, but before we proceed that with actual proof, let's look at a few examples of balls in these various spaces. So we already had the examples of the balls. These are the balls. So a bunch of examples already of balls in these metric spaces will give you. Well, we already have all the examples there, so there's really nothing to worry about. So the two examples that don't fall into this category are, say, circle, and X is the circle, and X is the sphere. Remember these? We just discussed that. So on the circle, we pick a point, and then this will be its. We just measure one distance, 1 r to the left and 1 r to the right. So if this is my r again, and say this is my A. Okay, so that's a ball, or whatever you want to call it. It is still an interval, just curved. It could be, if r is large enough, you will get the whole thing, by the way, right? So the same with the sphere, except it will be more like a disk. So if this is my point A is here somewhere. Okay, so I will have what, not strictly speaking a circle, but something like it, like this, right? So it will be curved naturally. So that's my disk, or well, a ball. So these are balls. measure distance from A to along the curve, and that will be the disk. So, for example, upper hemisphere is a ball around the North Pole. Okay, and then all of these are big ones. If you make it small, then it's almost like an actual disk. Now, the fancier thing is in a taxicab metric. Now let's investigate that. So, taxicab metric. Okay, so I pick point A here, and suppose let's pick R equal 1. So I want to measure distances, but I don't measure by straight line anymore. I measure it like this. Okay. Well, let's make it specific. Why make it more abstract than it has to be? How about I pick 0.11 on the xy plane, but they missed, and I'm talking about B. This is my A1. So an open ball radius 1 around this point A. Okay. So it's really uncomplicated to do if you don't want to guess, or you don't see what the answer is. Do you see what the answer is? Like that. So suppose this is 1, and this is 1. How large is the square? What? 2 by 2? Like this? Well, what is the distance to this? So this is 2, right? So that it's certainly not there, but this not this, but this yes. This one is these two are good because they have a distance of 1. So this is 1 and this is 1. All of these 1s, but the corners are not in. So if we're talking about closed ball, say closed. This is a closed ball. You put a bar above it. So. Can you guess what it looks like? Yeah, it's still a square, right? But it is just oriented differently. So this is the answer, actually. Yeah. Okay. Well, let's do it algebraically, just as an example. So xy. So that's my ball. Is xy such that what distance xy to 1, 1 is less than or equal to 1, okay? If I write out my distance formula, it will be simply x minus 1 plus y minus 1 less than or equal to 1. Okay, so if now you're looking at the border, of this, or boundary rather, of B1, it is x minus 1 plus y minus 1 equal to 1. Okay, so all you need to do is just to plot this thing, and I'm not sure if it is how clear it is that we're going to end up with this. So it certainly contains those points that I already have marked, these, okay, but well, I mean, I hope you can work it out. All you have to do is just to look at, you'll have 4 cases. 4 cases of whenever each of these expressions inside either positive or not. So positive, positive, negative, 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 positive, negative, negative, positive. Okay, and then 4 cases, each of the cases will produce one of those lines. Okay, but, well, certainly everything inside of that square will be included. So, okay, so they're squares. Then balls are in the space are squares with sides diagonal. So squares center, they're still centered at that point that we're looking at. Okay, so so it's very different, right? As we should expect probably, but if you think about it, there is some similarity in terms of the what we're aiming for, and that is the convergence. Okay, so just like with balls, we can use them as a kind of a measure of accumulation. So we make those disks small and small and small, and every time the tail of the sequence will eventually be there in that, no matter how small that ball is. So we use the balls or disks here, or intervals, but we could use these too. If you think about it, they're really not no worse at all. So they're we could measure that in circles. We can measure in squares. It's just as good. So that indicates that we are on the right track. So if we want to talk about convergence in this space, using these as balls is okay. Okay, so I guess we are out of time, and we'll just have to continue next time with better